Well, while we're waiting, why don't you tell us everybody who's here?
Yes, I would love to do that. Well, my committee almost is here. Dr. Jones and Dr. Ames are part of my committee. Then on the left, we have Ellie. She's our best friend. Miranda, she's my wife's sister. Then we have Dr. Hosky, Dr. Nelson, and the rest of us are students that we already know each other. And my wife right here on my right, in charge of the communications. Sage is there too. That's my daughter.
She's excited.
She's very interested in the bottle, which is good, you know. She's entertained. Yeah, I worked really hard on this presentation, especially to like create a good narrative. And so even though it might be very familiar for some of us, still like can get out there and understand what's happening. So I worked on some transitions that I hope, far from being distracting, they actually help me illustrate ideas that I want to get across.
Okay, we'll wait for Dr. Halgren to get going. So what you're saying is future MS thesis defendees, pay attention, this is really good.
I work really hard on this. That's all I'm gonna say.
Those of you who will be defending a master's thesis. I should say a joke or something.
Yeah, go ahead.
Some improv comedy.
So, Jerson should feel special because I normally don't wear a suit and tie to thesis defense. But I'm aware of the fact that he is also very active on social media, and that there might be photos of this event that turn up, so I wanted to look professorial.
Yes.
In such case.
Thank you.
While we're waiting for Dr. Halgren, I'll just say one thing about Jerson. So when, I think it was a good 3 or 4 years ago, I was teaching, as I recall, it was a intro programming class, and I was trying to transition this class over into Python, trying to do some new things. We were having fun, and then I had announced a couple of times that we would probably be interested in hiring students if they were interested. And Ricky and Jerson both independently came to my office on 2 different times and said, oh, wait, sorry.
Yeah.
I saw you here, but I pointed at Ricky and Jerson, so it's kind of fun that you're both still here. Came to my office and said, yeah, you might be interested in this. So you could do programming and engineering, is that a thing? I don't know if that was exactly the words, but basically that was the conversation. Is that, yeah, you can actually, we need good programmers in civil engineering, especially in hydroinformatics and water. So it's fun now to sit here and look back on, both of you have done so much cool stuff. And it's fun to have seen Jerson take advantage of being an undergraduate and getting involved in research, pass the word to the other undergraduate students in the program that, you know, it's a good thing to get involved in research early on. I think it makes your master's degree, obviously it makes it a little bit shorter, but hopefully it makes it very fulfilling. So it's been fulfilling for us and we appreciate it. Thank you. Okay, Dr. Halgren is here. We've done introductions, we had a donut, we had a little chit chat, so we're gonna go ahead and get started. And Dr. Halgren, would you mind kicking us off with a little opening prayer to get this started, and then we'll turn it over. Thank you so much, I appreciate that. Okay, so the way this thesis defense goes, many of you have already done one of these or are familiar with this, and so the way this will go is we'll give Jerson about half an hour to present his material. Generally, we won't have questions during it unless there's something obvious that there's a quick, clarification or something. But just to let Jerson maintain his pacing, we'll give you the half an hour to give us your presentation. And then I'd like to open it up to any of our visitors, which all of you students and family, to ask questions. Those of you online, if you have a question, you're always welcome to pipe in. And then we'll dismiss the guests, and then the committee and any of the faculty who would like to stay, we can ask additional questions, and then we'll go from there. That sound good?
Great.
Okay.
Thank you. Well, really means a lot to me to see you all here, so I appreciate that. I want to start my presentation by introducing you my family. Me standing here today, it's the result of the support that I've gotten from my family back in Peru and my wife's family, that now is my family. These are pictures of me with them younger. So I hope I'm honoring their name with my work. Espero que este trabajo sirva como ejemplo y que yo esté honorando el nombre de nuestra familia. I also want to recognize all my professors and peers that I had throughout my time here at BYU. And I want to do a special thanks to Dr. Hotchkiss for being a mentor in the hydraulics, in my water resources journey. I want to thank my peers and friends in the hydroinformatics lab for being supportive of this project. I want to thank Dr. Jones and Dr. Hagrin for agreeing to be part of my committee and offering your expertise on making this research more valuable. And I want to thank Dr. Ames for allowing me to work on this research and for mentoring me. And I want to thank all of you for being here and the ones that are joining online. Now allow me to introduce the title of my thesis. It is called Democratizing National Water Model Stream Flow Forecast through Cross-Platform Mobile Application Development. This is long, so what it means is making accessible the National Water Model through a mobile app that works in more than one platform. It's important to understand the context and the problem that makes this research important, like why this matters. We are aware that we have increasing amount of floods and droughts, and data to make it accessible, data is very much needed to be accessible for everyone, but more specifically for people who live close to rivers or work with them, like emergency managers, agricultural producers, recreational users, property owners that are close to floodplains. The challenge is that we have this data, but are they aware that this exists? That's the question. To illustrate this and the importance of this data, it's an image from the flash flood that happened in Texas in 2025 on July 4th. This is the aftermath and first responder coming to it. Now, to add to the context, I want to explain what the National Water Model is. And to do it, I have this image of the continental United States. Every green dot represents a USGS gauge. A gauge is a device that helps us measure stream flow on rivers, amount of water at a specific time. We have about 8,700 of them across the United States, and they cover 3.5 million miles of rivers and streams. This is great, but as you can see, it could be a little coarse, though this data is very valuable because measurements done on the ground. There are areas where we cannot access these values because those devices are not found there. That raises the need for a model that helps us access data where we don't have it. That's where the National Water Model comes in, covering in greater density, to be a little more precise, 310 times greater density than what we will have with the USGS gauges. They offer this through 2.7 million stream bridges, which give us stream forecast. So this is the National Water Model. Now, how does it work? The National Water Model is a system that uses meteorological data, like precipitation, temperature, uses the soil type to make predictions of what the forecast will be. Then it uses the USGS gauges for calibration and validation purposes. They provide us this data in 3 different ways: short range, medium range, and long range. They mean how far ahead are we going into these predictions? 18 hours, 10 days, or 30 days. Now, the next diagram is gonna help me illustrate this a little better. On the left part, we see observed data. This is what we will measure from the USGS gauge on the ground. From now on, we make predictions. The farther we go in time, uncertainty grows. In this case, this is a 30-day forecast or a long range. So the closer we get to the present, the predictions tend to be more accurate. But as we go further in time, the uncertainty grows. Now with this is a great tool, but there is an accessibility gap. This is the current presentation of the National Water Model through a web browser by visiting water.noaa.gov. This presentation is a great advance in this technology, but it presents some barriers. You will need technical interpretation to understand the time series data formats, your spatial knowledge. You need to know how to work with APIs to access more than one data if you want more than one stream, data for more than one stream. This presentation also doesn't allow any customization for users. It is the same portal for everyone who is visiting. And you cannot get push notifications. If you want to know what RIVR is doing, you have to go check it manually every time. This presents barriers for the general public, the people who this was intended to be serving. So, as an example, think of a youth camp director near a river. This person will need this data not just for today, but for the next week in preparation. Without a tool to bridge this gap, she will require expertise she doesn't have. Now, the National Water Model is great, but it has some limitations. The stream flow peak, there is a stream flow peak underestimation. What might be happening in the stream, the National Water Model might say like it's not as bad or it's not as high. It also, the National Water Model doesn't take into account human decisions. So urban and regulated basins are not taken into account in the National Water Model. And this is a model, it's not reality. So part of my research is not to improve the National Water Model or change it, it's taking it as it is and make it accessible to people. So to cover this problem, we have worked on a solution, a cross-platform free mobile app called RIVR. RIVR stands for River Information Visualization and Risk. This app was developed or built with Flutter and works on iOS and Android. Let me talk to you about how it works and the system architecture of this app, how this app comes to life. We have three very distinct parts of this app. On the left, we see the data sources that the app uses, the backend or the cloud as we usually know it, and the mobile app itself. I will go and explain each of these categories or phases individually. Starting with the data sources, we use three of them. One of them is the NOAA National Water Model API. An API is a way to request data from an outside source. We use it, we get the data by using a URL like the one shown above, and what we get in response are the values for a specific stream. The values look like this. They come in a JSON format. And as I explained, these values come for short range, medium, and long range. This is the API that we use as a data source. The next data source is the Cairo Return Period API. This API helps us classify the values that we get from the NOAA National Water Model API. Why is this important? 5,000 cubic feet per second in one river might mean flooding, while in another river, 5,000 might be just normal flow. So we need to, even though we get the same values, we need to classify. How do we do this? We receive return period values from 2 years to 100 years. These values help us classify specifically for each river what the flow is, and will help us plot it against those return period values for classification purposes. The last data source or external source that we use in this app is the Macbox vector tile. This is actually a great outcome of our research because we struggle displaying 2.7 million rivers on a mobile app. It will take minutes with many other ways. But Macbox helped us create vector tiles. Think of it as a picture where like the pixels flow with the streams and they adapt as you zoom in or you zoom out. It happens immediately to the human eye. Now that we have covered data sources, let's move on to the back end of Firebase. What is Firebase? Firebase is a product from Google. This product helps developers to not have to create or make their own servers for their apps. we are like borrowing their cloud, paying for their services. And some of the services that RIVR uses are authentication, Firestore, cloud functions, and cloud messaging. They make it super simple nowadays, where you can visit all these services through a dashboard or console. For example, this is how it looks, the authentication on the Firebase console. The next picture displays the Firestore. This is a database. All these values go into the cloud and you can easily visualize them that way. Then we have the cloud functions. These are functions that run on the cloud. We don't have to run it on the mobile, though we do it, but this will help us with the notifications feature of the app. They run 4 times a day to check, to request the national water model values, the Cairo return period values, and compare them. If the values exceed any of the return periods, then they will enable or trigger a notification which will be sent through cloud messaging. That's how it gets as a push notification on your phone. This is the cloud. Now let's get into the mobile app. As I mentioned, the mobile app was developed with Flutter, but how did we get there? How to make the mobile app was a big part of our research as well. What infrastructure, what technology do we use, what's out there? This work started with Travis Tyler. He was a great master student that I had the opportunity to work with as an undergrad. That was my job as a research assistant. He started developing this app, and he got to develop a prototype, but this prototype never ran on a phone. It was only on simulators. And in his prototype, he will display the rivers as pins. These are pictures that illustrate what his work, how his work finished. This is we would say the very first version of this app. Once he graduated, I took over and tried to do a build on that work. I wasn't very familiar with Dart, which is the programming language used by Flutter. So I struggled with it. I tried to use the WMS or web mapping service from HydroShare to display all these streams instead of pins, but it would take minutes to load. So this was a struggle that we had. So we decided to back up a little bit and use something or a programming language that I was more familiar with, like Python. This led us to Kiwi, which helped us create another working prototype that helped us use those API URLs and prove to us that we could use them. But the problem with Kiwi is that you cannot deploy those apps into phones like iOS or Android. These are images of what this app looked at that moment, made with Kiwi. Another version of this app. After everything we have learned so far, we decided to go back and use Flutter. This time, ChatGPT was new. We used it to help us write code, get more familiar with Dart, how to write this app. This took us about 3 iterations of like rebuilding again the app. Every time we improved the architecture of the app, and eventually we decided to work with Claude. Claude turned out to be a much better AI assistant for coding. The current version that is in internal test right now was built with Flutter and the help of Claude, and we decided to follow something called the clean architecture. Clean architecture is not something that I made up. This is used by software developers. We learned about it and we applied it. What does a clean architecture mean? We separate all the code that is in the app into different layers. So they are modular and independent from each other. I will illustrate this by going into each layer. The presentation layer. This is the thing that you see on the screen. Widgets, views, everything that you can tap on. That is the presentation layer. The next layer is the domain layer. This layer is in charge of doing all the calculations. Like it gets the values from the national water model, gets the values from the Cairo return period, and it does the calculation of like comparing them, and then it's sent to the presentation layer to be displayed on the screen. Next is the infrastructure layer. The infrastructure layer is the one that helps the app talk to the outside world. Outside world meaning or those data sources that I explained before. The infrastructure layer request the data, in this case, in this example, to the NOAA API, those values get back as JSON structure. This parse them meaning clean up the values in a way that can be sent to the domain layer above. So the domain layer can use those values, clean, and then make the calculations, and then send it to the presentation layer above to be displayed on the screen. I would like to show you what I used to build this app. The whole app as it stands now is about 43,000 lines of code between Dart language and TypeScript for the cloud functions. I use VS Code as my IDE. IDE meaning the platform that I use to write the code and organize my code into folders. If you want to have access and see how this code is put together, you can visit this GitHub repository. GitHub is like a Google Drive for developers. That way we can save all our code for easy access. Now that we have covered every single part of the system architecture and what makes the app come together, I would like to show you a diagram that will help me illustrate how this works together. So if we look at the NOAA National Water Model API, this goes to two places: the Firebase Cloud Functions for notification purposes, and goes into the app itself, goes into the infrastructure layer, domain layer, that's where the risk comparison logic happens, and then into the presentation layer or the screen of the phone. A similar, very similar route takes the Cairo Return Periods API. They're needed in the cloud, and they're also needed in the app, so they follow the same pattern. The next data source, as I explained, is the Macbox services. This one doesn't need much computing. They are ready, they are waiting for the app to request their help, so they can be shown on the map view of the app. Then the way how the notifications work is the following. We use the Firebase Firestore, where we store user preferences, like what units you want it to be shown on, CFS, like cubic feet per second or cubic meters per second. Checks what favorite rivers have been saved by the user, so we don't check for all the 2.7 streams, we only check for the ones that are favorites. And notification settings. If the user has it enabled, then we run it. If not, we don't run it. Once we get this data, that goes into the Firebase Cloud Function, which does the periodic monitoring. If anything gets triggered, we use Firebase Cloud Messaging that will enable a device push notification on the presentation layer of the app. I'm done with the deep stuff of the app. Now it's like the fun part where we can see how does the app look like. I have summarized all these features into 4 key features. One of them, the hydrograph and risk thresholds. This is how I can illustrate this by showing you the flow forecast overview. When you visit a river, you can see the current flow of that river, in this case the Blackwater River in Tuscaloosa, Alabama. 4,000 CFS for this river is normal stream flow. So the user doesn't need to have hydrology background to see that, okay, this is a normal stream flow. If they want more detail, we offer those three different ranges, short, medium, and long range, into these categories. We rename them into hourly, daily, and extended, so they are more familiar with any user. If you select, for example, the extended forecast, you will be presented with this screen, where it's a plot of how those values compare with the different risk levels. Again, to understand this, you wouldn't have to have a degree on hydrology or computer science to understand it. And this is the point of democratizing this data, making it accessible to anyone. The next key feature is the interactive map with tap to select. This is a great outcome of this research. We now have all these rivers presented on a map on your phone. You can just go to the river that you are interested in, tap it, and you get more details, add it to your favorites, check the forecast, just more accessible. The next key feature is the proactive flow alert. You don't need to open the app every time you want to check how the river is. If something interesting is happening, there is a monitoring happening in the background in the cloud. It compares the values, and if anything gets enabled or triggered, you will get the alert. And the last key feature that I want to mention in this presentation is favorites and personalized monitoring. You don't only add RIVRs to your favorites, but you can customize them. You can reorder them as you wanna, how you wanna find them. You can change the background, you can rename them. This is a great step forward into making this data, democratizing this data. Now, with developing an app and anything, you need to make decisions. If you select something, that means you are not using something else, right? Some of those decisions, the design choices that we made, are using Firebase. As I explained, this is borrowing the cloud of Google, use it as a service. Why did we use Firebase and not any other server? The reason is because Flutter is already a product by Google. So they produce a lot of documentation that help us develop. It made sense for us to stay in the same ecosystem, since Flutter and Firebase are both Google products. We also use the Cupertino design. If you see the app, it looks a lot like what the style would look on an iPhone. The reason we did this is because Flutter gives you a lot of power on designing your own widgets, and you can making us the way you want it. But that takes away our focus from the user experience. So we decided to borrow the library from iOS and just focus on using that library, borrow that, so we don't have to focus on designing our own widgets. The third deliberate choice is we are using currently email and password authentication. If you want to create an account, you can use it with your email and you create a password. Modern apps and other apps use Google or Apple, so that's something that we could add in the future as well. And we decided to do 4 checks a day, just to keep predictable Firebase costs, just a starting point, and see how things go from now on. Now, building the app is one thing, making it production ready is another story. To know if this app is production ready, we compare it to 6 different metrics: application size, startup time, memory usage, map rendering, API response time, and cache effectiveness. We ran this app on iOS and Android, and we measure those metrics. This slide shows you the values and the outcomes of those metrics, and on the right you see a graphic that represents those values. The hexagon, the gray hexagon, represents the boundaries of what could contain a production-ready app. The closer you are to the center, the better it is in production trials. As you can see, 5 of these metrics, the app met or surpassed what the industry requests from apps. One of them, the medium range API, did not meet those. It's recommended to have these requests to take less than 2 seconds. For iOS and Android, we were between 4 and 5 seconds. So this is one of the metrics that the app didn't meet. However, there is some good news on this. This is not native of the mobile app itself. It's more related to the national weather model and how long it takes to give us those values. So as the national weather model gets more efficient on sending those values, the app will get more efficient. So those are the results. What do they mean? We can come to the conclusion that the app is cross-platform ready. It works on iOS and Android, it's been proven. 5 of the 6 metrics meet the industry standards. As I mentioned, the network latency, that's just the ceiling. As the servers in the national model get better, the app is gonna get better. And we have used a clean architecture approach, which serves as a reusable template. We can use this approach for other applications in the engineering or science fields. Another great thing that comes from this research is that if we imagine all the features as Lego bricks, being from here down the current version, adding new features or replacing features It's like replacing Lego bricks or adding Lego bricks into the infrastructure of the app. So what does that mean? It means that any new feature would not disrupt what's already being built. It helps us as developers add new features without much complexity. Now, on the development of this app, there are some limitations. Some of them is that all the testing happened between writing code, and seeing if it ran on the simulator. There were not unit tests or widget or integration tests written on the source code itself, something that we can work on from now on. It was only tested on 2 devices, an iPhone 14 Pro Max for iOS and a Pixel 4a for Android. It could be beneficial to use it on, or test it on many more devices. We already explained the medium range latency. That's a known limitation. It exists right now. And there hasn't been any formal usability study, meaning this app hasn't been put on people's hands yet. It's only been put on some internal testers in the lab. Now, getting into my conclusions, I wanna remind us of the barriers that we recognized at the beginning, and how with RIVR we have found some solutions. Now we have hydrograph with risk thresholds that you can access from your pocket, on your phone. An interactive map that allows you to select any river in the United States. Color-coded risk indicators. You don't need a hydrology background to understand it. Favorites and personalized monitoring. You can add these rivers to your favorites. You don't have to visit the map every time. You can just go to your list of favorites and access them as needed. And proactive flow alerting. You don't need to check your phone manually every time to see how a river is doing. You can get alerts when there are interesting things happening. This is what users said. This is the feedback that we have gotten from our internal testers. Some of them are very positive. Some of them are things still to work on. Phoebe said that it really does remind of normal weather apps. This actually made us feel pretty good, because we're not trying to make RIVR its own thing. We're not trying to alienate it as its own grand thing. If we think of weather apps, more than a decade ago to what it is now, people have gotten very familiar with them, and there's a lot to learn from those examples. So that's what RIVR is trying to achieve. There are some things that we need to work on, like for example, we got the feedback that music gets interrupted when you open the app if you're listening to music. Those things are hard to notice when you are developing it, right? But that's why it's important to put it into people's hands to get that feedback. Future work. There is so many opportunities for this app. It opens the doors for democratizing more data. As an example, we could add USGS gauge integration. I explained in the beginning that USGS gauges give us the most accurate that we can get data for rivers. So if we put that in the river and we can compare how the National Water Model is doing with the ground level measurements, that would be very beneficial. We could add GeoGlows integration. GeoGlows is a global streamflow forecast. Adding it to another model will help us also compare these values and get access to these values, but not just for the United States, but for the whole planet. Formal usability study, as I mentioned, it hasn't been done. We need to put it on people's hands. We could add FEMA flood maps. This will be very important for preserving lives and properties, buildings. Also offline mode, so you could access this data, especially after floods and these events. Usually you lose connectivity, so allowing people to still check their values in an offline mode becomes very, very much needed. And automated system. This will help us catch bugs before we put it into people's hands. So with this research, we have been able to put 2.7 million rivers or streams into anyone's pocket. I want to thank you for your time, and with that, I'm open to any questions. Thank you.
Okay. So questions from the visitors, yeah?
So at the beginning, you said that flooding is more common, but also droughts. Have you thought about including any kind of drought warning?
Yeah. So the national water model does give you values for like droughts, very low values if they exist. We have not yet classified those. We don't have a classification for those. What is considered a drought. That's something that we definitely could add to future work. But the national water model just gives you a value, right? So it comes into the terms of like how do we classify? When do we consider something a drought?
Sujan just uploaded a new database of 2.7 million streams, and their 7Q10 low flow drought is one of the metrics. So where did you go?
Right.
here.
So
So that could be used, yeah.
yeah.
So I have computed the various percentiles and also various other low flow metrics also that can help for drought information. So, and that is readily available through the next version of the API.
That's awesome. That's an example, actually, very good example of the scalability of this architecture. Adding that is just adding one more data source and plug it through the pipeline of infrastructure, domain, and then presentation layer.
Questions?
So my question is about the notification.
Mhm.
Do you give notification in certain timestamp, or is there any level of risk associated for notifications to pop up in mobile app?
Yeah. The only case where I would see that being beneficial is on flash flooding. Flash flooding can happen in minutes, in an hour. The national water model produces, the short range produces new predictions every hour. So there is a possibility those could get caught, and those are things that we need to learn as we go. Maybe 4 times a day, maybe it's not enough. Maybe we need to increase it to 5, 10 times a day, or continuous checking, which will require more computational level in the cloud level, right? But that's a good consideration that we need to start learning from now on and see how the app work, how the app performs once it is in people's hands.
I have another question, like you said that the forecast has the uncertainty bounds. How could we communicate it to the people through the mobile app?
The forecast has, sorry?
The information about the uncertainty, how do you communicate to the people?
Uncertainty?
Uncertainty.
Uncertainty.
Yeah.
That's a good question. There is uncertainty in the national water model, so we need to add disclaimers into our app. The national water model, again, it's a model, and there will be uncertainty as far as you go in time. So we need to make it clear that this doesn't replace hydraulic studies. Serves as a first level assistance to the users. As the weather apps do, they are not accurate all the time. They serve as a first level assistance, which will need or require more in depth, right? So, yeah.
Kind of to Tamara's question, do you show like uncertainty bands right now in the app?
Yes, I do.
Okay.
You can see it in the hydrograph view of the app. You can toggle on or off the ensembles.
With the hydrograph, can a user zoom in? Okay.
Yes, they can do. That was another outcome of our research. Initially, the hydrographs were static, but now we use a library that allows us for users to manually zoom in into the values and select and see the values at any time. Yes.
So you mentioned how the app, excuse me, you mentioned how the app makes this data accessible to the general public. Do you feel like it also educates the general public on how to interpret and how to use this data?
I actually feel, yeah, I agree. I think it does. As engineers, the way that I would consider national water model right now is that it's being built, but not everyone has access to it, right? And it requires professionals and people that know about it to educate the population. So as engineers, we don't build for engineers, for other engineers. We build for the public. And this is what this app is trying to do. I think we're missing the last mile of things. We haven't made it accessible to the public. So to educate, you need to be very familiar with the background knowledge, right? So I feel like as engineers, it's our responsibility to use that knowledge and express it in simple terms, which is what RIVR is trying to do, to educate the population.
How about your online guests, if you have a question?
Any of you online have a question?
Jerson, it's Brian. What plans do you have, like a continuation of the last question, what plans do you have to get it into the hands of those that need it? Maybe that's not an engineer's job, but are there plans for this app to advertise or to do something that gets it into the hands of the camp director or anyone that might benefit from this?
Thank you for your question, Brian. Yes, that's the ultimate goal, to put it in people's hands. And you're right, this is not completely engineering. This requires the assistance of more professionals, marketing and stuff like that. We are right now in internal testing phase. As we keep improving our app, our goal is to put it in people's hands, hopefully pretty soon. That's what we're working on. Thank you for your question.
Okay. Phoebe, you want to say something?
Dr. Nelson, have a question?
I have a question, because I can't stay too much longer.
Oh, okay, all right.
But I'm just curious, like, with respect to these questions, like, where are things at with the National Water Center, like, in terms of making available? I would assume that's the best way to get it in people's hands, are the ones who are using that, or the National Weather Service offices, right, the river forecast centers, are they confident enough in the national water model that they want all that information out there like that?
Yes.
That would be my question.
Yeah, the approach we're taking with this is, and I'm gonna use an analogy. The reason why most of AI is booming right now is because most of these developments are made open source. So people can get their hands into it and improve it and see it, what it's not doing really good and make it better. We have the national water model right now. Kind of feels like it's locked behind us. Like it's not perfect, so let's keep it away from the people. But if we do not see where it's lacking, there is gonna be a limitation on knowing how to improve it. So I think the way to go about it is making it accessible, but as it was mentioned, let's put some disclaimers on it. Let the users know that, hey, don't use this as the ground truth. That's what's gonna happen. It's impossible to predict what's gonna happen. Use this as a guide. So it is important to make the National Water Model available with those disclaimers.
And also, we have a proposal sitting with them right now. And if it gets funded, that means, yes, they do want this data going out to people. If it doesn't get funded, I think that's a clear statement that we're not ready for the national water model to be in people's pockets. And I won't be offended either way. I will be, actually. I think we'll both be offended. But that'll be like a very clear statement. If they don't fund this app for the next round of Cairo, then it's like, okay,
We're not ready.
we're not ready. We'll put it on an obscure website that people can fumble through. If they happen to get the data, great. But we don't want it this easy. At least that's kind of how I'm interpreting that proposal. Okay. Well, thank you, guests and friends and family for being here. And I guess we will excuse everyone that's not part of the committee. Well, obviously, you're welcome to stay. We'll give you a 5-minute break, Jerson, and then we'll have our committee discussion with you. Okay? So we'll give you just a 5-minute break.
Okay, yeah.
Everybody, please take a quick pause.
I need it.
Thank you.